Hello all. In this video, I am going to discuss a case study on fault location of overhead transmission lines. So generally we know there will be many faults occurring in the transmission line due to external disturbances and due to weather conditions. So in this case study, I am going to discuss about the introduction to the faults and current methods of fault location calculation and drawbacks of the current methods and what is the next implemented method, that is magnetoresistance sensor method, and we are going to have a conclusion. So before going into the introduction, what is fault point, where the fault has been occurred? So we have two towers, in between we have a red line where the fault has been occurred. So there is a sending end voltage and a receiving end voltage, that is ES and ER. So from where we get electricity from any power station. So power stations are not located nearby, yes. So it is 100 and 200 kilometers far from our place. So from that far place, we have to bring the electricity to our place. So the power generation station, we call it as sending end, and our place we call it as receiving end voltage. So during the transmission line, if the fault occurs, so that is the fault point where the transmission line is between two towers. So what is basic introduction about the fault? So what is fault location and detection? So in any power system and transmission and distribution subjects, fault location and detection is very important. So fault location and detection is very important in case study of power systems. So the traditional systems adopted for fault location are, we have two approaches: traveling wave based approach and impedance measured based approach. And now the implemented, since there were many disadvantages in traveling based approach and impedance measurement based approach, and we next go for magnetosensors and are used in finding faults in the transmission lines. So what are the two methods? So impedance measurement based approach and traveling based approach. In impedance measurement based approach, the voltage and the current pre-fault and post-fault voltages are analyzed, that is before pre-fault and post-fault voltages. So based on the voltage levels, that particular approach will give the where the particular fault has been occurred. In traveling wave based approach, here it is based on the frequency range, and the technology used in this approach is time domain reflectometry. This is the technology used in this approach. The fault occurring on the cable will generate both voltage and current traveling waves with wide band signals. So based on that value, we are going to analyze where the fault point has been occurred. So what were the two disadvantages and what were the drawbacks before going into the newly implemented technique? The parameters of the lines has to be known. Yeah, without knowing the voltage and the current values, that particular approach will not find out the fault position. So have to consider that the line is homogeneous, relative location error is very large many times, and performance is highly dependent on signal processing techniques, and these two techniques are of high cost. This is the main drawback of that particular two approaches. Next we will go into magnetoresistance sensor. So it is a sensor which senses where the fault has been occurred. It was discovered by William Thomson in the year of 1856. That is this tendency of a material to change the value of its electrical resistance in an extremely applied magnetic field. And this is that particular sensor where it has magnetizing property. It has a magnet and an MR sensor, that is magnetoresistance sensor. In this magnetoresistance sensor, we have three types: an anisotropic, giant, and tunneling magnetoresistance. So this is of different applications. So anisotropic magnetoresistance, giant magnetoresistance, and tunneling magnetoresistance, we call it as AMR, GMR, and TMR respectively. Coming to magnetoresistance sensor, what happens when a fault occurs? So when three-phase short circuit occurs, that is nothing but a fault, occurs, the magnetic field will be increased. So the ratio of the magnetic field of the fault to that during the normal situation is the same as that of the ratio of short circuit current at the normal condition. Yes, fault and short circuit are equal. The ratio of magnetic field during the fault and the ratio of short circuit current during the fault will be same. So at this point, I'm going to generally tell you some point. So generally in a transmission line, we will be having three types of faults: line to line, line to ground, and double line to ground faults. That is between two lines, or line to ground, or two line to ground. This will be the basic faults, and this sensor will sense based on the at particular point we will be fixing that sensor, and it will sense that the particular location. Before we had two techniques, but using the techniques also we can find out, but we cannot find out the exact location. We can only find the range where that fault has been occurred. But when we go for sensors, we can exactly find the fault point. This is the main advantage of the magnetoresistance sensor. So this is of low cost, high sensitive, and larger temperature range, and wide frequency bandwidth. And coming to the assessment, which of the following is not an unsymmetrical fault is line to line fault is not the unsymmetrical fault, and dash can be defined as an abnormal connection of very low impedance between the 2 points. So can anyone guess what will be the answer is? And so as a conclusion, we have discussed about what the fault occurrence in the transmission line and the techniques used before in order to find out the fault point, and now a magnetoresistance sensor has been used. Thank you.